So today we will start the one algorithm. This is the randomized search algorithm, that is the genetic algorithm, and this is one of the area of the subcomputing. Okay, subcomputing has that there are two areas in the computing. One is the hard computing, another is the soft computing. Hard computing means it's a pure mathematical analysis. Whatever the result you will get, you have to get through the mathematical derivations. That is called the real analysis derivations. And another area is called the soft computing. In the soft computing area, there is no such rigorous math to be required, and we are having some tools of the soft computing. One is that neural network, another is that fuzzy, another is the genetic algorithm. Okay, so today our topic is to genetic algorithm, how to find out the optimal solutions of a complex equations. Okay, so here we can start. So first, what is the genetic algorithm? That is the genetic. That is the definitions. And genetic algorithm is a randomized search and optimization technique guided by principle of natural genetic system. Now, what is called a natural genetic systems? That you know what is the Darwin's principle. Darwin's principle of reproduction and survival of the fittest. Okay. Here that means that the fittest one can survive in future in the next generation. And those who are not fit, those who are the worst in the sense, they will be discarded or they will be demolished. Okay, so that genetic algorithm is a randomized search and optimization technique guided by the principle of natural genetic systems. Genetic system means that what I told you, that is the Darwin principle of reproduction and survival of the fittest. Recently, there has been a great deal of interest in genetic algorithms and their application to various engineering fields. That the genetic algorithm is not an area of the computer science or information technology. It can be applicable in any branch of engineering. For example, that you can apply in the image processing, you can apply in the wireless network, you can apply in the chemical process, you can apply in the industry 4.0, you can apply in cyber physical system. So there are many ways that to apply the genetic algorithm to find out the optimal solutions in a real-time system. So here GA is being applied to a wide range of optimizations and learning problems in many domains. Okay. GA also lend themselves well to power system optimization problems. I told you that it has to be applicable in various engineering areas. Since they are known to exhibit robustness, it is called robustness, require no auxiliary, and can offer significant advantage in solution methodology and optimization performance. So here the thing is very crucial that since they are known to be exhibit robustness, that's that whatever you are doing, whatever solution you are getting using the genetic algorithm, it may not be exact optimal, because it is a randomized search, it is a probabilistic algorithm. So you may not get the exact optimal solution, whatever you can find out in using the deterministic algorithm. There are so many deterministic algorithms already you have learned that for say dynamic programming, divide and conquer algorithms, so those are branch and bound algorithms. So there are so many there you are getting the exact optimal result. But genetic algorithm, as it is a randomized search, but sometimes what happens that you must have to use this kind of algorithm to find out the quicker solutions of the problem. And even it is may not optimal, but it is very closer to the optimal solution. It is very close to optimal solution, and how much it is close, it depends upon what is your precision level, what is your accuracy level. You may say that solution, whatever I will find out, it may be the 4 decimal places, or it may be 2 decimal places, it may be 6 decimal places. So it depends upon the situation, it depends upon the problem, what problem you are going to handle. Okay. So here, and it requires no auxiliary informations. You know that is, you have done the maximum minima in the class 12 or class 11. That maximum minimum, whatever you are doing to find out the maximum and to find out the minimum, that you are making the first order derivative, and that first order derivative will be equal to 0. And this is the protocol, this is the rules to find out the maximum minimum. And after equating to 0 to the first order derivative, you are getting the solutions of x or y, whatever be. And then you are going for the second order derivatives, and whatever the value you have found of x in the first order derivative equating to 0, that values you have to put it, and if it is negative, then you can say it is a maximum. If it is positive, then you will say it is a minimum. But whatever the maximum minimum you are getting in this solution, that will be the local maximum minimum in some neighborhood. But here, genetic algorithm, there is no information. It is not a deterministic algorithm. There is no hard and fast rule what you are doing. It depends upon your expertise. It depends upon your findings. What exactly you want to do. That you will discard the worst chromosomes, worst solutions by replacing the worst solution by some new solutions, or you have to go for the genetic operations. That genetic operation, the two types of genetic operations are there that will run afterwards. One is the crossover operation and is the mutation operation. Normally two types, but there are some other operations are there. So, and can offer significant advantage in solution methodology and optimization performance. Okay. Now next, the main advantage of the GA, what is mentioned here, formulation is that fairly accurate result may be obtained using a very simple algorithm. That algorithm is very simple because there is no hard and fast rule that how will you proceed these algorithms. Here, that is that results may be obtained using a simple, very simple algorithm. So as it is not a deterministic algorithm, you don't have to follow that a set of rules, set of steps in a sequential manner. So here, that GA algorithm depends upon that randomness, how will you find, and you have to find out that how much close you are to the optimal solutions. And according to that, you can change your strategy, that what you will do in the next time for the genetic operations to find out the next generation, to find out the offspring of the next generations. The objective of the fitness function is a judge of GA's attempts. GA do not know. We are having the objective function. What do you mean by the objective function? The function you want to optimize, either to maximize or to minimize. Okay. So that is the GA do not know how to derive a problem solution. The genetic algorithm doesn't know that how it will solve the problem because there is no hard and fast rule. It depends upon the users, how you are thinking about these solutions. It depends upon. So my steps and your steps may not be the same for the same problem, but the result will be the similar. Whatever you are doing, whatever I am doing, that result must be close to each other. Okay. So GAs do not know how to derive a problem solution. That is very important point, but they do know from the objective function how close they are to better solution. So you have to understand that how close you are to the final solution, final optimal solution. That you have to understand whenever you are in the intermediate stage of your algorithms. Okay. Now the question is that when will you terminate the algorithms? So there are, each and every generation is called in the computer programming, we are calling it is an iterations. So iteration 1 means it is the first generation. Then you are producing the offsprings for the next generation, and that will be the iteration 2. So how long you will continue to run these algorithms? That is the question. Then you have to terminate the algorithm, or you can assume that after 200 iterations or after 200 generations, we have to stop the algorithm because we cannot continue after 200 iterations. So you can stop it. You may not get the optimal solutions after 200 iterations. So another thing is that is the best way is that you have to assume some level of precisions before solving the problem, before initiating the problem, and that precision levels means it depends upon the problem. Sometimes you can say that I will take the precision level up to 2 decimal places of accuracy. And in some problem you can say that I will take the precision level up to 3 decimal place, up to 4 decimal place, up to 6 decimal places like that. So like that here. So whenever you will say that the 2 consecutive solutions of the best of the lot, having the, if you have the precision level say up to 2 decimal places, and whenever you will find that in 2 generations the best solutions are same up to 2 decimal places. After 2 decimal places, it may be something else. Then you can stop the algorithm. So it depends upon the precision level when you will terminate the algorithm. Sometimes it will take 200 iterations, sometimes it can take 500, sometimes it can take 1000 or 2000 or 5000. That doesn't matter in such a days whenever that your machine is highly configured. And next, that slide is that sometimes near optimal solution that can be generated quickly. using genetic algorithm, and that is more desirable than optimal solution, which require large amount of time. You will see that whenever you will use the deterministic algorithm, for example, dynamic programming, for example, backtracking algorithm, for example, branch and bound algorithm, you will see even you are getting the most accurate result to find out the optimal solution, but the time complexity is very high. So that time complexity, whenever it will be very high, it may not be applicable in a real-time systems. So to apply that algorithm, that searching algorithm in a real-time system, sometimes the genetic algorithm is very much required. Even it will not only to reduce your time complexity, but at the same time it will give the optimal solution. May not be 100% optimal, but whatever the solution you are getting for the reduction of the time, that may be accepted in some engineering problem. Okay, so that is desirable than optimal solution, which require a large amount of time. Now the next point is that using GA problems can be modeled as optimized problem. So GA is a searching algorithm which mainly to be used for the optimization problem. Genetic algorithms work with a coding of parameter set, not the parameter themselves. Because whenever you want to find out the solutions, that you want to get the solution as a decimal value. Okay, but genetic algorithm doesn't work with the decimal type of number. It will be converted either in binary bits or in hexadecimal bits or in octal bits, like that. And therefore they can easily handle integral or discrete variables. So whatever the things, suppose you want to find out the solution x from 0 to 50. So what we'll do in the genetic algorithm, whenever an fx is a not exactly continuous function, or it may be continuous. It may be continuous function or differentiable function, or it may not be continuous. There have some discontinuity in the domain of x. There may have. But genetic algorithm is not bothered about that. Why? Because whatever be the functions, whatever be the domain of x, that genetic algorithm, that the first job is to divide the whole domain of x into a many number of discrete intervals of equal size. So whatever the things, that it will convert the whole thing into a discrete manner. So even the function is not continuous, may have some discontinuity at some point of x, or it is not at all continuous, or it is continuous throughout the domain. It doesn't matter, because it will subdivide the whole range into a equal size of discrete range. And what is the size of the discrete range, subdivided range? That depends upon the size of your chromosome. Chromosome means that whatever the solutions you are getting in each and every generations. That chromosome, it can be in binary bits, can be in hexadecimal bits, can be in octal bits, like that. Okay. GAs can provide globally optimal solutions. That I told you, that is the one of the main advantages of GA, that it will give you the global optimal solutions for a given range. Objective function means that function what we exactly want to optimize. That is called objective functions. And from the objective functions, that we have to evaluate the fitness value. The fitness value, that whose fitness value is less, that is the worst. They will not survive for the next generation. So either you have to replace those solutions by some new randomized solutions, or you have to go for the genetic operations to replace them, or you have to keep it. You may have to keep it for the genetic operation with the good evaluated value of chromosomes. Like that. That depends upon what you will do. There is no hard and fast rule. Okay. So not derivatives of other auxiliary knowledge. Therefore, they can deal with the non-smooth, non-continuous, and non-differentiable function that I told you in a previous slide. GA use probabilistic transition rule, not deterministic. It is not a deterministic algorithm, so no deterministic rules to be followed in genetic algorithm. These are the states: a population of individual, each with an associated fitness value. That a first generation population you have to choose randomly. Operators, that the operators transform the population into new generation. Then it will produce the offspring for the new generations. using Darwin principle of reproduction and survival of the fittest. Then Goldratt's criteria for terminating the search. That criteria I told you when you will terminate the algorithm. Whenever you can find out that whatever the precision level up to 2 decimal places or 5 decimal places, whenever you will found that is same in 2 consecutive generations of the best solutions, then you can terminate the algorithm. So you can accept that result. This is the final result. Now, representation of the scheme. This is the formalizations. Before solving the problem, you have to formalize in such a way. Representation scheme, how to represent the decimal solution into a, either in binary solutions, what is the size of the binary bits, what is the size of the binary solutions, initial solutions, that you have to determine first. You have to determine and that depends upon your level of precisions. Your level of precisions. What will be the size of it? If your level of precision is very high, suppose you consider up to 4 decimal places, then chromosome size is, say it is 25. You want to get the higher accuracy of your solution, say up to 10 decimal places, then the size of the chromosome may be 50, 60 or 100 like that. It depends how much accuracy you want. Whenever the accuracy is increasing, the size of the chromosome will be also increased. Size of binary bits, number of binary bits will also increase. Parameters for controlling the algorithm, fitness measures. So each and every generation we are evaluating the fitness through the functions. That function is called the objective function. The lower fitness value of the solutions we like to discard or we like to replace in the next generation. Parameters for controlling the algorithms. So whatever the parameters that you are using to control the algorithms, so that you have to assume before starting the algorithm. Now this is the way that how can I represent a decimal solution into a binary bits. Binary represent consists, you know, that is 0, 1 binary bits will be there, and suppose this is the one of the solutions, and you know how to decode this binary bit into a decimal value. Say for example, if this is a one number with the binary bits, then what you are doing to decode 2 to the power 0 into 1 plus 2 to the power 1 into 1 plus 2 square into 0 plus 2 cube into 1 and so on. Isn't it? Why are you multiplying by 2 to the power 0? Because binary having the base 2, either 0 or 1. For the decimal it will be 10. This is one of the examples that you have learned in the first year. Say suppose 11 is a decimal number. How 11 has to be converted into a binary bits? Because it is required for the genetic algorithm. So it has to be divided by 2, remainder is 1. Then 5 divided by 2, remainder is also 1. 2 divided by 2, remainder is 0 and it is 1. So what will be your binary? Equivalent binary numbers of number 11, 1, 0, 1, 1. How? This is 1, this is 0, this is 1, this is 1. So 1, 0, 1, 1. Now suppose this is a function with a k number of variables. Each of xi is having the domain, having the range. The lower bound is ai and upper bound is bi. And this function is the function for all xi in di. Di means di is the range, di is the domain for xi. We wish to optimize the function f with the required precision, say up to 6 decimal places. Suppose I am considering a problem and I want the accuracy up to precision level of 6 decimal places of accuracy. Then what I will do? Then di each and every, I told you that whatever be the range of xi, that has to be subdivided in equal size of so many range. So if it is ai and bi, then if I want the precision level up to 6 decimal places, then the whole domain must to be subdivided into how many number of this bi minus ai into 10 to the power 6 equal size range. Suppose I want the precision level up to 2 decimal places of accuracy, then bi minus ai into 10 square, like that. So that the whole domain of xi has to be subdivided in equal size range, and how many number of sub-ranges, how many number of discrete domain, that bi into ai into 10 to the power 6. And this is the way that how to determine the size of the chromosome. Chromosome means in a binary conversion, I am saying, for each and every solutions. Suppose I am having a precision level up to 6 decimal places. So bi minus ai into 10 to the power 6 number of discrete, equal size discrete domain, subdomains. Now this is the inequality, that inequality 2 to the power m, and it is less than 2 to the power m and greater than equal to 2 to the power m minus 1. So for which smallest value of m that will satisfy the inequality, that we have to compute. What is the smallest value of m that will satisfy this inequality? It may be 2, it may be 6, it may be 10, it may be 12. And suppose that m is equal to 10, that means what? That means that your binary numbers having the 10 number of binary bits. Say 1 0 1 1 0 0 1 1 0 like that. It depends upon the number, what number you are choosing. So then mi be the size of the chromosome. So you have to find out that is very important thing before starting the genetic operation. What will be the size of that how many number of binary bits will be present for your equivalent decimal number. Okay. The equivalent value for mi bit string can be obtained as, this is the formula. That means, so why it is required? Because you got the binary conversions of the initial solutions. You understood that how many number of binary bits to be required, what is the size of the binary bits for each solution. Then what you will do? So first generation is done. Then in the first generation you have to calculate what is the fitness value. And whatever the function you have mentioned, say x square minus 3x plus 2, this is the function you want to optimize, you want to maximize or minimize. For what value of x, it will give you the global maximum for x is equal to suppose from 0 to 10, like that. So what you will do, then again you have to convert from binary to decimal value. And what is the calculation? XL, what is XL? Suppose a is equal to 2, b is equal to 5. So what is your XL? XL is equal to 2 plus 5 minus 2, because upper bound, x is the upper bound, x from 2 to 5, 5 minus 2 divided by, suppose m is equal to 10, 2 to the power 10 minus 1 multiplied by decoded value of string. Decoded value of string means, what do you mean by the decoded value? Say for example 1011, what is the decoded value? 101, come from the right hand side, right to left, 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 square plus 1 into 2 cube. That is called the decoded value. So that is the decoded value. So you will get the value, what is the decimal value of x from the binary numbers. And that value of x you will put it in the function x square minus 3x plus 2. So for all the solutions you will get like that. And from there you have to calculate that which one is the fit chromosome and which one is the not fit chromosome. As you are maximizing the value of fx, that means that which will how many number of chromosomes give the good values, good maximum value of fx, and what are the chromosomes they are not giving, they are giving the poor value of fx. So the solutions which are giving the poor value of fx, that you have to discard, either you have to discard or you have to replace by good chromosomes, and that good chromosomes may come from the randomized way. Randomly you can select, or you can go for the genetic operations with the good chromosomes and bad chromosomes to improve the solutions in the next generations. So that depends upon you what you will do. So now the fitness measure. Fitness measure, I told you fitness is equal to f, that function for what function you want to optimize for this regard. And the character represents in S is also referred as chromosome. So chromosome, each and every solution I am saying it's a chromosome. We are using the term of chromosome. Now parameters for controlling the algorithm: population size. Population size you have to determine according to your problem. Maximum number of generation in a run G, it depends upon you, that when will you terminate. It mainly depends upon your level of precision. Number of runs. Selection and replacement strategy. Selection means what chromosomes you will select for the genetic operations to produce the offspring in next generation. That you have to select. Selection and replacement strategy. There are many kind of selections in genetic algorithm. Selection function to identify the result. So what selection procedure you will consider, that you have to identify. Now you see that initial population to be selected randomly. Initial population always you have to select randomly. That I have shown you that with a number of 11. Okay. So like that, say suppose you have considered that your size of the binary bits is suppose 10. So 10 binary bits you have to select randomly. You draw a random number from 0 to 1. 10 times you have to draw a random number. Say suppose first number is 1, put 0. Suppose second number is 1, it is 1, so 0, 1. Up to 10 bits that you have to consider. Third binary number, suppose it is 1, so 0, 1, 1, like that. You have to select. G times or less, evaluate the fitness function of individual. Then you have to evaluate the fitness function, and which one is the fittest, that you have to consider as a first priority to produce the offspring, and which one is the bad chromosome, not giving the optimal value, very low value like that for the maximizations. You have to replace them. Evolve the population, randomly select individuals and randomly apply operators among reproduction, crossover, mutations. Okay. So you have to select the parents to produce the offspring. Why we are producing the offsprings? To get the improved solutions, to get the better solutions. Select the fitness individual as a solutions. That fitness value to be calculated. Run the GA many times. Many times means many number of iterations. As long you are able to, until or unless you like to terminate. Now GA operates through a simple cycle of stages. First, creation of population. That population to be selected randomly within the domain. Then after selecting that, you have to evaluate. I told you. First you have to convert into decimal number again with this formula, and then you have to put it in the objective function, the function you want to optimize, and you have to calculate that what maximum value you are getting. Selection of the best string. Best string definitely you have to select, because best string having the maximum priority to go for the genetic operation to produce the offspring in the next generation, and genetic manipulation to create new population of strings. Now you have to go for the genetic operation to create a new population of strings. So now that a very important thing is that last one, to implement the genetic operations. So this is all the cycle of the genetic algorithm. So first you see population is chosen. It is chosen randomly. Then fitness value. You have to put in the function, those random solutions, and to find out the fitness value. And here there is a reproduction. Reproduction means there is a they are being ready. Which chromosomes are being ready to produce the next generation offspring. So it will go to the mating pool. And another line is that population chromosomes, they are considered as parents. And you can consider few pair of parents. It may not be all chromosomes. Few pair of chromosomes as a parents. Suppose there are 100 solutions initially you have chosen randomly. Out of 100, maybe 50 chromosomes you can go for the genetic operations. 50 chromosomes means 25 pairs. Okay. So they are being ready in the mating pool. Now mutation is done, manipulation is done. Now manipulate means either what type of genetic operations will go, at what partitions that crossover will be done, what is the rate of the probability of crossover, maybe 0.25, maybe 0.5, maybe 0.1. As it is a probabilistic, so it will always from 0 to 1. But normally we are considering for the crossover rate or crossover probability from 0.5 to 1. We are considering. Now for the genetic operators means either crossover, mutations, or maybe complement or something else. Now offspring has been generated, and in the next generation those offspring, that means those child, whatever they have produced, they will be considered as a population. Then they will be considered as parents, and in the next generation they will produce some offspring for improvement of your solutions. So this is the whole genetic cycle, entire procedure. Each cycle in GA produces a new generation of possible solutions for a given problem. In the first phase, an initial population that you had seen, you have to choose the population randomly, describing representatives of the potential solutions. Finally, they will produce the offsprings, and after few generations, you will get the final result. And that is called a potential solution, is created to initiate the search process. The elements of the populations are encoded into bit string called chromosome. Okay, each and every chromosome, we are calling it as a chromosome. So performance of the string bits, that binary bits, that chromosome, we are calling it string. It is called a binary string, often called fitness, is then evaluated with the help of some functions. Function means whatever the function is given, what you actually want to optimize. Okay, representing the constraints of the problem. Depending on the fitness of the chromosome, they are selected for a subsequent genetic manipulation process. That process can be the crossover operations, can be mutation operation. It should be noted that the selection process is mainly responsible for assuring survival of the best fit individuals. So which one is the fittest chromosome? That you have to always give the priority. Priority means that always you have to dose chromosome into a mating pool, into a genetic operations. Because if you consider the worst chromosome, so their offsprings may not be good. It is expected from us. Their offsprings will not be good because they are very weak chromosomes. So whenever they will produce the two offspring, it is a high chance it will not be good. So whatever be the which are the fittest chromosomes in the current generation, that we will consider for the genetic operations. Now this is the first genetic operations, crossover operations, that recombines the bits of each two selected strings is executed. Various types of crossover operators are found in the literature. The single point, normally the two crossover technique we are using, one is called the single point crossover and that is called the 2-point crossover. And the crossover points of any two chromosomes are selected randomly. Second step in the genetic manipulation process is termed mutation. There is another genetic operation which is called a mutation. In the crossover operation, two parents are required to produce the two offspring, but for the mutation operation only one parent is required and it will produce only one offspring. And how it has to be done, that you will see it in the example. You see, that is the crossover in genetic algorithm. Suppose there are the two chromosomes, two parents are there, and how many number of bits? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bits. Here you see parent number 1, parent number 2. In some current in current generations, parent number 1 9 bits, parent number 2. All the chromosomes have the equal bits. Otherwise, genetic operation will not be done. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I will go for the genetic operations, crossover operation to get the offspring. Offspring means child of the next generations. Now how will you go for the crossover? It is a randomized search. So each and every step you have to use the random technique. So as there are the 9 bits by 9 binary bits, so you have to put the location from 0 to 8. 0 to 8. Now you have to draw the random number from 0 to 8. Suppose it becomes 3. It can be 4, it can be 5, whatever be. Suppose it is 3. Then what you will do? Then you see here 0, 1, 2, 3. After third bit you are making the partitions. You see that arrow. After the third bit 0, 1, 2, 3. Here also 0, 1, 2, 3. So that partition is done. Now What will be their offspring? Offspring, you see, this is the child 1, this is the child 2. You see the child 1 that the first 5 bits 11010, 11010. This 110, that is same, exactly same, that part, that particular part. So that part, that particular part of the child, first child, is inheriting the characteristic from parent 1 up to this part. And what about the second part, 1001? You see 1001 of the parent 2, second part. So that the first part of the child 1 is inheriting the characteristic from parent 1. And second part of the child, of the first child, is inheriting the characteristics from the parent 2. So whenever you are saying, what is the concept of the inheritance? A and B are the, I am saying about the multiple inheritance. You know what is called the multiple inheritance because you have done the OOPS. Multiple inheritance means that whatever be the subclass, that subclass will inherit both the property of the superclass. So here also you see that the child 1 is inheriting some property of the parent 1 and it is also inheriting the some other properties of the parent 2. Similarly, you go for the second child. Your random number is 3, so it has to be partitioned after third bit. See 10101, 10101. So you see 10101, it will be same, the first part of the parent 2. So that means this part is inheriting that child number 2, second child is inheriting the property of the parent 2 up to this part. But as it is a child of both parents, so some characteristic must to be inherited from the parent 1 also. And you see 1010, that is the second part of the parent 1. So these two childs are inheriting some characteristics of parent 1 and parent 2. That is the concept of the inheritance. Okay, so this is called a single point crossover. Why it is called a single point crossover? Because partition is done in a single point after the third bit. It is called a single point crossover. And you go for the 2-point crossover. Sometimes you are going for the 2-point crossover for the better convergency of the solutions. Now you see, here you see there are the two parents. This parent, parent number 1, parent number 2. Parent number 1, how many number of bits? 1, 1, 0, 0, 1, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 bits are there. Parent number 2 also 14 bits. Both the parents must have the same number of binary bits. It has to be same size, otherwise genetic operation should not be done. Okay, now, so 0 to, say size is 14. That means you have to draw the random number from 0 to what? 0 to 13. 0, 1, 2 up to 13. So there are 14 bits. Now you have to draw the random number from 0 to 13. Suppose you got the random number 4 and 8. Suppose you make it something else. Suppose you are getting the random number 4 and 8. So where will be the partitions of the two parents? After 0, 1, 2, 3, 4, after 4th bit, there is a 1 partition and here it is 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. After 8 bit, there is another partition. Similarly for the first parent also, after 4 bit and after 8 bit. Now, how they will produce the offsprings? So partition has been done in 2 points, 4th and 8th positions. That now you see that the first child, that is the first offspring, you will see that 10101, and so those up to this part it is inheriting from the first parent. Say same. Now you see the middle one, 1110, where it is coming? 1110. So up to so this part is inheriting from the parent number 2. Here you see for the second child 01101, that will be same as up to this part of the second parent. And 100, where it is coming? That characteristic, that particular characteristic is coming from the first parent 1001. So 1001, and it will be also the same 1101, 1101. So that means that both the child 1 and child 2 is inheriting the property from parent 1 as well as from parent 2. Okay, so those solutions is the new solutions. Those offsprings will give you the new solution, and it is expected it will give the better solutions. It may not be always better, but as these two parents are one of the fittest chromosome in the current generation, so they will produce some good offsprings. So these are the new solutions you are getting in the next generation. Similarly here also, after genetic operation, and that genetic operation is called a crossover. And here you see, this is the mutation. I told you for the mutation case, only one parent is required, not two parents. And here you see how many number of bits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bits. Again you have to draw the random number. For where you will mutate the parents to produce the offspring, suppose it is 5. So 0, 1, 2, 3, 4 and then 5. So 5, so those bits will be interchanged. If it is 0, then it will become 1. You see it is 1. If there was 1 here, then it would be 0. For 1, it will be replaced by 0. For 0, it will be replaced by 1. It is called a mutation. So this is the offspring that has been produced from this parent for the next generations. So these are all about the genetic operation. One is crossover, another is the mutations. Now this is the crossover rate that I told you, as it is a probability. So probability, as it is a probability, it always in between 0 to 1. It may not be negative, it may not exceed 1. So this is the calculated in GA by finding out to some fixed population, and typically for the population size 30 to 200, crossover rates are range from 0.5 to 1. What is the meaning of 0.5 crossover rate? Suppose there are 100 chromosomes. So how many out of 100, how many will go for the crossover operation? 0.5, that means half. So 50 chromosomes will go there. 50 means how many pair of parents? 25 parents, 25 pairs. Okay, so 0.5 to 1. Similarly for the mutation rate is the probability of mutation, which is used to calculate number of bits to be muted. How many number of bits to be muted? Suppose there is a 10. That binary, it is 10. That the size of the chromosome is 10. 10 number of binary bits. So how many bits to be muted? That is the question. So the mutation operator preserves the diversity among the population, which is also very important for search typically. So that is also important. The simple genetic algorithm uses the population for 30 to 200 genetic rate, mutation rate is 0.0012, maximum 0.5. That means half of the population. So half of the populations you can conduct the the mutation operator. Okay. So this is all about up to mutation rate, and we will continue in the next sessions to complete this particular topic. Okay, so thank you.